Oops, sorry, I forgot that my audio was turned off. My screen is visible, right?
Yes.
Okay. So today would be like official session 2. And after this, next session, probably we'll do distributed training based on interest of people, but taking a month's time to, to reiterate and actually interact with HPC and run a couple of AI jobs. And then maybe if you come up with your own workflows, we can look into how to optimize your workflows and showcase that to others in the group, which is like the end goal of today's session. Yeah. So I'll skip the introduction. And as for today's quick agenda, we'll just quickly go over what environment setup we talked about last week. And then I'll simply run a couple of jobs using Visual Studio Code and show you how to use different tools like Grafana, XDMod, Slurm, and NVIDIA SMI to see how you can actually monitor your job, the performance, how your job is doing based on the allocation that you're requested for. And how do you take the observations out of those logs and rechange your batch script so you can reduce the cost of your jobs. And then I'll show that entire thing with Ultralytics example mode and some best practices on how you can manage training data, how you can use entire compute node that you're requesting for to speed up your training job or speed up your, not just training job, but basically speed up your any workload that you're running on HPC. So again, those who are new to this session who haven't done the survey, please do this survey. So we'll get more stats on the information that you need. Like anybody on this call who haven't done the survey, I'll paste this in the chat. And then please complete that survey. So very quick overview. Today we'll be working again from login node and compute node, but most of the time we'll spend our time in the compute node trying to access files that are stored in the file system versus accessing files that are local to the compute node while we are running training jobs. So that is a quick overview of what we will be doing today. So as recap one, I have shared the YOLO OSE setup guide, I believe yesterday. So just go over that and set up Conda environment. Because we won't have enough time for you all to do the environment setup in this session. But if you already have the setup ready, you can run along with me and try different things and stop me if you're stuck somewhere. Or you can take this after the session and try setting up the environment and running Ultralytics code. And I'll share you the zip file and the sample images after the session so you can run the experiments. Maybe run it even more wild by modifying the number of CPU cores, how you allocate number of workers to your data loader and other things and play around with it. So key notes that we have to remember when we are actually talking about setting up an environment is, let's say I have an environment that I have installed my Ultralytics, my Python and everything. You don't need to do those steps again and again for every job that you run. So you just set up environment once and you can run 1,000 jobs if it's using that environment. So treat that environment as a path of readable executables. So multiple jobs can look into that environment and use those executables in one go. So you don't need to recreate environment for every job that you run. And same thing like in the last session, we saw by creating different environments with, like, for instance, we were creating an environment without CUDA, and the Ultralytics picked the latest CUDA version and installed it. But then we also saw another configuration where you selected which CUDA that you want your GPU to use, like say CUDA 11.8, and you saw that that was the environment that Ultralytics was using, as opposed to CUDA 12.4, which it by default installs if you haven't mentioned any CUDA. And then we also saw how we have set up IPUI kernel. So, your collab nodes can actually run notebooks in that environment. So one tip is, like, let's say if you have selected a CUDA version and then set up your own environment and installed IP kernel, you can use the same environment to run jobs only in CPU or GPU or with collab nodes in different modes. So you don't need to create multiple environments. You can have a superclass environment with all the libraries you want with different interactive mode and use that environment across different setups. So As I said last week, we were talking about setting environments, but every job that you're running, you still have to load these. For instance, let's say I want one compute node here, and I want to run my job, one job here and one job here. You still have to set up environment. You don't need to install and configure it, but you still have to, you don't need to install and set up the environment, but you have to configure your job saying, hey, if you're running code here, make sure you're running my X environment. If you're running code here, make sure you run X environment here. So setting up or configuring the environment before you run your job, you have to do it across every job that you do. So to simplify that, you just have to run or look at code like this with every job that you run, and I'll show how we do this in both interactive and batch mode. So here we're not doing anything. Every time you log in into a system, every time you request a new resource, by default, OSU will give you only the default modules or libraries that you guys would need. So if you need CUDA, you have to load CUDA again. And as I said, by default, it'll direct your Conda path to your home directory as opposed to the one that you installed. So you have to reconfigure and say, hey, here is my new Conda. And then you can start executing your workload. You don't need to install softwares again and again because the environment already has it. All you have to do is for every job, you just have to tell where your environment is. So here are a couple of commands like to figure out what modules are installed, what CUDA is needed, what Conda environments do you have, because you might set up 5 different Conda environments. So every time you may not remember the name of your Conda environment. So you can use Conda info n environments and see what environments you have and pick one directly, as opposed to installing environment every time you run your job. So I'll also share these commands after the session today. So before we go and figure out how to check the health of the environment, so let's reiterate on connecting with uh, Visual Studio. So let me first terminate this session and I'll open a new session. So this is like a fresh new terminal or fresh new interface of my Visual Studio. Here I'm going to my remote sessions and I'm connecting to Ascent. Like here, since I already connected to multiple different folders, all of them were cached into my Visual Studio locally. But in case you haven't done it and it's the first time doing it, you could do like start with a session. You can simply come here, click either here and say, go for a session, or you have connect to as a shortcut here, or you can go to this one here that shows terminals, remote explorer, and connect SSH. So I'm trying to do that and I'm saying I'm connecting to, and I'm connecting to a remote host, or I can connect to a remote file server, whichever is convenient for you. So I'm saying connect current window to a host. So what I'm trying to do is I'm just taking this window as opposed to opening a new window and connecting it to an Ascent cluster. So here, it's trying to make a connection to my SSH on the right that you see, setting up SSH host. And here I just enter my password. Sometimes if you have multi-factor authentication, like a passcode or anything, it'll ask you for your passcode that you have to enter after you enter your password, if you have configured multi-factor authentication with OSC. So now I have connected to my remote server. And if I actually open the terminal window here at the bottom, you see you are in Ascent now, as opposed to your own local system or local host or local box. So now let's connect to a file system. Let's open a file system and I want to open FS, ESS. FS is file system, ESS is project space, EAS 2271 is the folder inside my project space. And we went over these configurations in the previous video. So go over and look at how you access which folder path you want. And I have a folder called Swathi, so I hit here. And I say, okay. So now it's opening my file system. Now you see my entire file system. And for context, for those who were not here last time, let me open a new window. and show you what my file systems looks like. So essentially, as again, reiterating here, you'll have different file systems. You'll have shared scratch space, project space, and your home directory, like these spaces here, like home directory, all the scratch space files and all the project space files. And I literally chose to go here inside my Visual Studio. And I'm here. So these were a couple of files I was working in my previous sessions, so the files got opened up. And this is my terminal. So if I do pwd here, I'll literally see that I'm inside this particular folder here. So now we are here. So the first thing I wanted to show you guys is, again, in requesting resources using batch mode, or sorry, interactive mode. So how do you do that? So basically you ask for an S allocation. You say you want one node and you say number of CPU cores, and we'll talk about this in a couple of slides. But essentially number of CPU cores, you say, I just need 10 CPU cores. I don't need many, but I need one GPU because I want to run some training jobs. And this is the project. Like you guys will be assigned to your own project. So you have to tell which project should be built for this particular task. And then how much time you want a particular node. So once I do this, once I ask for it, don't copy the $, but after the $, and hit enter. So just to get on screen. Yeah. So I'm automatically granted, and I'm automatically now instead of login node. So here, if you see, I was in a login node. So once I got my allocation, I'm automatically moved into my login node. So earlier, I was physically present. Let's say I was logically present at login node, but now I'm logically present at this compute node, which is called A0212. So that's my login node. So now if I do PWM, I can still see the file system. So earlier when I was accessing or doing PWD, which is like print working directory, it literally was going from here, going here and printing your working directory. But now you're here. So from here, it is going here and printing your working directory. So you see that how you're trying to access file system over the network that is within the cluster. So this is essentially when we figure out where we store our training data sets when we are actually running a training job. So if you have any questions, please post them in the chat and we'll answer them. Or you can raise your hand and also ask. So don't hesitate. So, so with the raise of hands, can I see how many of you guys are following with me or how many of you guys are just taking notes and want to follow later? So whoever is following with me, so I can go a little slower. Okay, looks like everybody is taking notes or wanted to do later, so we are good. If you feel the pace is super fast, let me know. I can go a little slower. So now we talked about environment setup and how to run. Now let's go back and see how I'm setting my environment. So now I'm in my login node. The first thing I want to do is I want to list if CUDA is available because I want to run my code on a GPU for which I need the CUDA libraries. So if I do module list, you see that I have Intel, I have Mbapage, I have modules, but I don't have CUDA, which is essentially the GPU way of running tasks on a system. So that library helps GPU to run tasks. So you don't have CUDA library. So now let's load CUDA. So if you don't know which version of CUDA that you want to load or what is the exact name that you want to load, you can do module spider. Sometimes you can try SPYDER. That's like the older command. Now they changed it to SPIDER. So either would work. Because if you say SPYDER in the newer environment, it says it's deprecated. So you can try both and see which is working for your environment. So here you see, I wanted to load 11.8 because I used 11.8 while installing my setup last week. So I'll do module load this. I think I didn't copy. So module load CUDA. So this is what I'm doing. So now if I do module list, I have CUDA loaded into my path folder. So now I'm good. Now all I have to do is I just have to source. I don't need to do the entire setup that we did last time. All I have to do is just source the path. set the environment variable, source my path, like where I have my conda. So I have my mini conda set up here in this session, and I have to activate the session that I want to use. So for now, let me first source my mini conda. So here I'm sourcing it. So now my path, or basically my execution endpoint, knows from where I have to read the executables. So now let's see what environments do I have and what environments do I want to activate. So if I type conda, so here you see ton of environment because I have mini conda installed multiple places. But the current source where I loaded, these are the ones that are super active. Currently, this base is active. This is the current base that I see in the command line. Base that you see here, this is the one that is active, but you can also run this particular command. Let me go back here. Conda info. So you have another command called conda info. You can type that and see which conda or which mini conda is actually loaded into your system. So if you type conda info, you should be able to see the entire description of which mini conda you're running. So here, obviously, the one that I loaded is this. This is base. But if you, let's say, are in another login node. So I just opened another terminal. This one, if you see, I'm still again back into my login node. I'm not into the allocation. So now if I type conda info, I would be seeing something very different because I haven't sourced conda in this particular terminal, because this terminal is, let's say, another job that you are interacting with HPC. So here, if you see, oh, I think we got back because we opened it from the same terminal. It was taking a parent one. So let's go into another terminal here. Cluster, SN cluster here. Since I was opening the new bash terminal from the same Visual Studio, it's borrowing the environment from the previous one. So here, if I see conda list, which is not sharing anything with my Visual Studio, you'll see different. So you see that it's picking my conda from my home directory as opposed to the path that I set. And it's also base because base is like the default conda environment it uses. So now I will want to activate. Now I want to activate this one, which is basically a GPU installation. Wait, I'm wrong. So yeah, I want to activate this environment, which is basically my GPU with CUDA, and also it has like notebook, PyKernel setup for the notebook. So I can activate this here. And now if you again type the same conda info, instead of base, it will show you which environment you're using currently. So at any point, if you're not sure which conda you're sourcing to, just you can use conda info and you'll get all the information. So now my environment is set up and I have my job allocation. I'm running my job allocation. This is where I'll take you to a wonderful tool that is configured here at OSC is called Grafana, which will literally help us see what is my current allocation, how am I utilizing the resources that were given to me. So if I see the resources that I asked for, like I asked for 10 CPU cores and then 1 GPU core. So now I want to see to what extent am I using these. And remember, we are doing nothing. We are just in the shell terminal of that particular system, and we have zero, or we are not using any compute or any utilization at this point. So now if I go to this dashboard called Grafana, not.osc.edu, you guys can also go and see which node, like my node allocation. You don't need to have the allocation to see here. As long as you have login credentials with grafana.osc.edu, whatever jobs that I'm running, you can see how it's performing on your screens as well. So if I see HPC job metrics, I go here because I want to see just my job metric. And I want to know what is my job ID. So one way to know what your job ID is, once you are in the system, you can say echo $slum, I think. I hope I'm not getting this wrong. Yeah. You just have to echo slum underscore job ID and you'll have your job ID. You can copy this job ID, come back here and copy that here and hit enter. But here you see I'm not in cardinal cluster, I'm in ascend cluster. So I just have to go to ascend. and hit enter. Oh, sorry, I think I still copied the wrong one. So, yeah. So here you see, I mean, since I just got the resource allocation with last 24 hours is useless, let's say last 5 minutes, and you'll see a decent amount of some interaction happening. Not much. The CPU utilization is barely there with user. You see my user interaction of CPU is like 15% of 10 CPU cores that I asked for. But if I see my GPU metrics here, I'm barely doing anything. Like my GPU is not active because it's 0. See, GPU memory is 0, GPU interactivity is 0, because I have not done anything on GPU yet on that particular allocation. So one might ask, what if you're not in this node and it's a bad job? In that case, you don't know what job it is. Then you can go to on demand and go to jobs. And I'm opening in a new tab for convenience. So I can go to jobs and see what jobs I have. It'll take a little bit of a time to load it here, but you'll get your job here. And you can see the job ID from the web portal. Or there's a command for it. Let me quickly grab that command for you. So basically, this one, what's this? Yeah, see, currently, if you see, if you can see my screen, you can see the job ID. So from the UI, you can grab the job ID. And you can see which account, you can see most of the information. And you could probably also see the command that has invoked this particular. It's showing the output location where I'm located at or where I have asked to execute the job from. And also you can see detailed metrics here. If you hit this detailed metrics, you'll again land back to the Grafana page. There are also other ways of looking at it called XD mod. So this OpenXD mod will have more micro information about your job, how efficient is your job. For instance, let's look at the job that I ran today, which is July 7th. One issue with XD mod here is it has stale information, like you have to wait sometimes for a day for your job to show up here. So today I'll not see any of the jobs that ran today, but I can see the jobs that I ran in my previous session. So in the previous interactive session, that's when I've interacted with OSC and I see these are my jobs. You can see how much memory is allocated, how much wall time is allocated on all detail metrics. More, you'll see more per job wise tailored detail metrics in XDMod. So if you want to wait and come back for a day and then see XDMod is your place to go. But if you want live data and live stats about your job, go for Grafana. And on demand will literally take you to both XDMod and Grafana and a go. So any questions so far? Okay, with a show of hand, I know a couple of people in this call have used OSC before or HPC before. How many of you guys have not used it even till today? Because I know we have a group of people who are pretty new to HPC. Okay, cool. So if we actually go to the command line and say, hey, okay, this is one way to find my job ID. Then another way to find my job ID is on demand. But is there a command line way to actually find out what your job ID is? You can simply use something called SQ, and $user is basically your username. And you should be able to see what jobs you're currently allocated with. So for instance, my job username is Swathi VM, so I can still do that if you know. Either way, $user is like a variable that holds your username. So each user automatically, this particular variable gets assigned to your usernames. Same like $home path that we saw last time. So now you have your job ID and now you know how to look at Grafana, at least like the basics of Grafana. Let's go ahead and start running the jobs. And before running the jobs, I'll quickly explain what I'm trying to do with my training job. So here is my very simple training script with Ultralytics trying to trail a YOLO model for object detection. And I'm taking several factors like what model type. So YOLO Ultralytics comes with several generations of YOLO. And here I'm just mentioning which generation YOLO and what model. Is it like a small model, large model? Like how BERT comes with different models, YOLO also comes with different sizes. These days, all foundational models and all state-of-art models come with different sizes. So you can pick what size of a model you want to train based on the resource availability or based on where you're deploying the model. So I'll tell that here. I'll tell where I have to store my output results, which is like intermediate weights. So Ultralytics literally stores the weights after checkpoints it. So in case your job gets terminated, you still have some checkpointed weights and nothing goes waste. So where you want to save and how many epochs, basically batch size. And then data YAML is where I actually have my training data sets and also test set because I'm trying to run and test a couple of things here to see how my model is doing. So where my test set is located. So now if I have to run this job, since I'm already in the allocation, I'll run it this way. Because I'm providing all these values as command line arguments, I'm just saying, hey, I want YOLO 11 large model and save it in my OSC. So this is the account. And I created a folder called profile demo and save the results here. My data set is actually located somewhere else, which is not in this folder. So here is where my data set is. And here are the test images that you want to test and score for the model that you're training. So now we know when we look at the structure and when you notice that everything, including like where you're storing, where you're reading data, is in my project space. ESS is the project space. So if I go back to this beautiful diagram, I am storing everything here. So I'm basically storing the results here, reading the files from here, and reading the data set from here. Everything is happening via the file system server. So it's happening from the shared file storage. So now let's, another command that is of importance that you might be interested to know is time. The time command will literally tell you how much time your particular job has spent in different modes, which is system mode, user mode, and kernel mode. And let me see if I can quickly give you an overview of that before running it. So yeah. So basically, when you type time Python like train.py, you would see how much time. Let me quickly run that so you'll have a better understanding. So I'll go epochs 1 and batch size. Let me do a bigger batch size so we run faster. So now inside my, so I'm running this inside my allocation. So this should be technically using my GPU. And I'll also show you how to validate if you're able to see the GPU. But first, let's use the time command and see what output we are getting. Okay, so yeah, I'm in the wrong folder, so I have to go to CD, OSC, and then run from here. Yeah. Oh, I think not also from here. It says, okay, no such file or directory. Okay. So I have to go profile demo. That's where. Okay. Oh, wow. Sorry. I think I'm in the wrong, I'm still in the login node. So that's why it's causing the error. So I have to go back to my execution node. Here is where you see the difference, right? So this is a classic example where I have not loaded my environment and trying to run something and it says pandas not found because I'm not in my environment and the base environment doesn't have pandas. So this is the node, or this is the instance of the node which has everything loaded and set up in the path. So CD was demo. So copy and run. So while this runs, there are a couple of commands that you could see. You could literally type like CUDA visible devices with like, this is another environment variable, same like $home or $user. It shows where all the devices that you have access to on this particular node. If this will print like an empty line, for instance, we can go into the login node here, and the login node doesn't have any CPU. So if you press enter, you'll see that it's empty. It's not giving you any result. But if you use the same command here, I'll show you once this job runs. Oh, I think it will take a bit of time. It just started. So you can see several things, like basically it's trying to load the model, load the network. This is all Ultralytics doing behind the scenes. It was trying to see what we are trying to do and stuff. I'm using a third-party tool called Ultralytics to train my model. So yeah, it's pretty quick. Yeah, I think there's like, yes, Amit, that's a good question. So login node, when people set up like OSC, they will not set up very powerful nodes, but they'll rather set up nodes which has many CPU cores, so it can handle many users. The test case for login node is handling multiple users in one time. So let's say 80,000 users are logging into OSC, they'll be having login node. So and to handle, let's say 80,000 users or say 30,000 users, if you actually type SQ here, SQ WC-L, it will tell you how many jobs are there. Currently on Ascend, there are 908 jobs. So imagine 908 users logging in. So the login node should have the load capability to run 908 nodes. So you have compute capabilities for load, handling load, heavy load, which are tiny login jobs. So in login node, you're not supposed to run any jobs, any heavy jobs like training, data processing, or data viewing, because you're then overworking the login node and they'll not even let you, they'll not give you enough resources. They'll only give you enough resources to interact with Linux commands, basic Linux commands. Whereas compute node is the actual node where it's not for like 10 users using the compute node, but one user running heavy compute intensive jobs. Like you can literally do data training, data visualization, like weather data, black hole simulation, you can do anything on compute node. So the both are compute heavy in their own ways. For login node, it's more about stress or load testing, but compute node is more actual compute power, which comes with CPUs, GPUs, and TPUs, and whatever, or tensor cores, whatever. Did I answer your question?
Yeah, makes sense. But also follow-up question is, so you said number of jobs are equal to number of users?
I mean, it may not be. I'm giving you the worst case scenario where each user has one job. There could be like
But
one user can have 10 jobs, right? So
yeah, that's what I wanted to know. One person can have multiple
multiple
jobs
jobs.
running,
No,
right?
I was just telling the worst case scenario where let's say each user has a job, then the load
Mhm.
testing, because when we test a particular node, for load, we have to go with worst case scenario, right? How many, what's the likelihood of more users? So for instance, here I am also an Ascent node, but let's go to our dashboard. Let's go to our file system here quickly. And let's go to another cluster, say Pitzer. This is new Pitzer, upgraded one. So now let's do SQ. SQ is basically number of jobs running. You can also, I think you also have a command to see how many users are logged in into the login node, but so SQ, because you don't need to enter the login node to submit, right? You can be in dashboard and submit, and even dashboard internally creates, like whenever I'm connected to a dashboard and a file system here, I'm still connected through the login node. My interaction through the entire system here happens through the login node. Whichever mode I chooses, either if I'm on my file system, like just viewing file system, that happens through login node. So login node use case is to have as many users as possible. Ron, would you want to add anything more to that?
I mean, there's a lot I could try to say. Is there a specific part you want more input from, or is regard to on demand?
Sorry, Ron.
Sorry. Is there a part of that related to on demand you want me
Oh,
to?
no, no. I'm just saying, did I cover the purpose of compute for login versus compute node?
Yeah, yeah.
Compute in terms of HPC compute, not the term compute. So for instance, now let's see here, let's go for Pitzer. And if you want to know the configurations of login node and stuff, all you have to do is go to their website like osc.edu, type Pitzer, go to the Pitzer homepage, and they'll clearly give you what is the actual compute hardware that is there behind the login node and compute nodes. So here you see, right? So even your on-demand or login, everything goes via login node. So literally when I'm here, I'm having one instance of the login node. So I'm probably one of the users of the login node.
So how do I know whether I'm in login node or I'm in on the compute node?
So here, if you see, I can see @0212. So I'm inside my compute node. This is the, if it's A0212, it means that ascend 212 node. So that's the naming. But if I see something like this, @ascend-login 01, it means that I'm in the login node.
I
Like,
see login node has login in it.
yes, and it has full name, ascend. So Pitzer-login, ascend-login. Whereas if it's Pitzer, let's say 360 node, then it will be P0360. And this is like you manually, when you ask for interactive mode. So what happens is when you ask for an interactive mode, like S account, that is an interactive way of asking jobs. This is how I request for an interactive job. So if I use this command, I will be asking a node and I'll be telling them that give me this node and please move me from login node into that node. So just with this command, you are getting the resources for yourself. If you actually top here and I ask for this, when I ask for this, I'm actually going into this node. Like it's testing if I have whatever I'm used, am I having access to add in this node. Then I automatically move from login node when I'm requesting it. Sorry, I think here. Yeah. So when I asked for this request here, it's actually it says pending job allocation, job granted, waiting for resource configuration. Node, this one is ready for you. And after this point, it's literally taking me logically from login node and logging me or moving my terminal from login node into that node. So I'm automatically logged in. And from here, where I was here at login node, after this SLOC, I'm directly moved into my allocation node. So I'm literally moving from here into here once I get the allocation. And this is interactive mode because I'm in this mode itself says, hey, give me a node and make me feel as if that's my own system. So I'm interacting with it in live, like how I'm submitting jobs, how I'm testing the jobs and stuff like that. Whereas there's another mode called batch mode, and I'll talk about it or I'll show you how to submit that in a while. But in batch mode, you will not ask a account like this. Rather, you'll create a file like this, submit batch.sh, and inside the batch, whatever you're saying here, like how many nodes you want, how many codes you want, you tell that inside that particular job. And here is where you say, hey, this is my job. Give me this job name. Put the output, because since you are not in interactive mode, you have to tell that. In batch mode, what they do is they take your code, they get a node allocation, run your code there and store the output in your folder or wherever you ask it to store. Since it's not interactive, you can't interact with that particular node while the job is running. So you have to pre-configure what interactions has to happen on your behalf on that particular node. And you have to tell that in a script called like the batch script.sh or whatever. So in this script, the first thing you're saying is, hey, this is what I want. Like I want these many GPUs, I want these many cores, this much hour, and this is the account that you have to bill me. The same thing that you're telling here, but in a different format. And then you say, once I get this allocation, here is where I can literally say CD and say, let me go here and say PW. Usually from whichever path you are running, or say you say qsub or sbatch this particular file, that is the command to run this particular mode. And wherever path you're doing, it starts running from that path itself, like that endpoint itself. So here you can literally say this CD this. So as soon as you get an allocation, your terminal, this particular command get executed, you get moved into this folder, then code. So whatever I did manually here, after getting the allocation, the system will do on my behalf. The script will do on my behalf. So the script will load this module, it'll load source my conda, it'll do this, it'll print whatever I want it to print into my output file. So it prints into this output log file that I tell. So all the shell commands, like for example, here I'm doing ls, right? And it's showing in my graphical interface. All these things will be automatically outputted into my output folder or error folder based on the type of result that I get from running these scripts. So these are bunch of shell scripts, but they get executed one after another inside the batch mode where you don't have access to. So you have to pre-tell what has to be run. So it will run from top to bottom and within this allocation time and give you the results as output or error files or wherever you want your outputs to be written as part of scripts. So in this case, you will not be able to see which node it is, but you can see what node it is by running commands like sq and see, hey, you have submitted the job, you want to see which job. And then if the job is still running, you can still SSH into that job node. I'll show that to you. It's an interesting use case. I'll show that after I finish talking with a couple of slides. But at least for now, is it clear, Amit? The difference and how you know which node you are at? Okay. So now we ran the time command, right? In time command, you see times like real, user, and systems. This becomes really important, especially when you're trying to optimize your code. So what real time is, like I really found an interesting way, GPT gave me really interesting answers for this. So real time is nothing but like a stopwatch time. So let's say you have 5 relay, have you ever played this relay race where there'll be 4 runners participating as one team and they complete the relay by passing on a baton or something. So similarly, stopwatch is like from the start to the end, how much time the entire circle took. Whereas user time is basically nothing but time spent for executing each code. For instance, let's say four of us in this call have to count money. So we can split and count money quickly. So if one person has to count like 100 bills, they take 100 seconds. If 4 people have to do, maybe they take 25 seconds because workload is distributed. So in that case, real time is 25 seconds because from the stopwatch to end watch, we were able to finish it. But the user time is individual user time, which is 25 plus 25 plus 25 plus 25, which is still 100. And system time is probably the time it took for some, let's say a team leader who was distributing notes between these 4 people. So what is the time it took for the team leader to distribute the notes? So something similar. So in the context of HPC, when you actually look at this one here, real time is nothing but the overall time it took for my code, this code to run. Whereas user time is the time it took for each of my CPU core to process whatever information. So here, this job is a GPU run job. So CPU literally runs for only processing the input data. So how much time each core overall spent processing the information. Sometimes this one could be more than real user, which I think in one of my examples we can see. So here you see the real time is 2 minutes, but the actual user time is 4 minutes because user time, as I said, is like based on how much parallelism happens. Each parallel user is or each parallel core is considered as one full operation, and you just sum it up. So you see user time more than real time if you're using multiple cores. And then the next thing that you see is obviously system time, which is very less than the overall real time. That is the time where the system is using to maybe load your code into the compute node from your storage node and other things. Essentially, you have to still move your code that is literally sitting in, my code is at FSS, right? So it's here, it has to move from here to the compute node and stuff like that. So it's the system time, which is outside the compute time. So these times will give you an overall, I mean, the current job that I'm running is super tiny and easy, so it's okay. But when you run complex jobs, these times will give you a better understanding. And we'll see a couple of subtle differences using that. So coming back, I also wanted to tell you whether you want to see if your job is running in the CPU or no. So in that case, there are still commands to see if you have GPUs enabled. So as I said in the login node, when we actually ran this command, like this is your login node. And when you ran this command, you saw nothing. But now let's run this command in your allocation node. See, you see 0. So basically, in the world of computer science, indexing starts at 0. So 0 is like the first GPU that was allocated. And since we asked for only 1 GPU, we got 0 GPU. If it says 0, 1, it says you have 0 and 1, two GPUs, and so on. So Ascend, I think, have 4 GPUs per node. So you can request up to 4 GPUs in a single node. Ascend, I think now the new Ascend has both 4 and 2. So if you want to know, hey, how many GPUs can I access? All you have to do is again go back to the system here. For instance, in this system, if you look at standard node here. Yeah, some nodes have 42 nodes and some has 32 nodes. So which some configurations. So this one is 40 cores. So you can go only max up to 40 cores. So currently I'm asking like 10 cores. So you can go up to 40 cores if it's Spitzer, this set. And if you ask for 44 cores, they'll give you another queue. So based on what you ask, they'll give that particular node to you. So since this is Spitzer, let's go to SN. That's where I am at this point. So if you want to know, hey, what are the maximum limits? I'll come back to this again, but I just want to give a very brief overview of GPUs. So here you see, oh, interesting. I changed it. Or did I come to the wrong one? Send. Yeah, new page. Yeah, sorry. I went to the old page of Ascent. This is a new page of Ascent. So here you see, and these nodes here, you can literally see that each of these nodes have 4 NVIDIA GPU cores. So you can ask up to 4. And if you ask like 4, they'll allocate you this compute node. But if you only need 1 or 2, they'll most likely allocate you node from this because there are like 250 of these nodes. So if you ask for 2 nodes, most likely you'll get an allocation from this node, and you can go up to 2 in this. So again, it's all about how well you can read the documentation and how well you understand what are your job's resource requirements. So now that we have seen that it is running on GPU, and we also saw how to use Grafana. So now let me go back and run a job, much longer job. So let me go 16, not 32, and let me run it for a little long time, like say 10 epochs. And again, the same. So here I see, here my files are still stored in the file system and my job is running. And let me run this here again, and let me show you what Grafana would look like for this execution. I have to copy better. So now my job is running here. So imagine this is this terminal. Now from this terminal, as I said, you are in login node, right? But you want to go and see, since your job is already running, you can't use parallel command prompts because already your current terminal is involved in running a particular job. But if you want to run tools like NVIDIA SMI, you can't run from login node. So basically NVIDIA SMI, if you have to run NVIDIA SMI, you have to be in the node that is running your job. And NVIDIA SMI is like a monitoring tool that is that is provided by NVIDIA to profile how your job is doing against the NVIDIA GPU. So you literally have to be in the node. But now in the interactive mode that we see, our current node is already occupied and you're running your job. So you don't want to quit it. So that's when you can go into your batch job and you can simply do SSH and this node. So you know which node you are in. So the node you are in is called 02A0212. So all I'm doing is I'm just saying SSH from my login node into this one. Since I have access to this node now, I'm opening another connection into my login node. So currently in the compute node, you have one connection made. So now you're making another connection into your login node to run parallel command. So now you are inside the CPU because your GPU is still working and your GPU is working on your job. So now since you are in this node again, parallelly, like using another terminal. So basically you're making 2 connections into the same login node. So now I can do NVIDIA-SMI. And I can see all the information that's currently running. So my job is running and I can literally see how much memory my job is consuming, how much power it is utilizing, what's the current GPU utilization my job is having. And if you want to see if this is correct information, we can also go back to our Grafana. And here we are already seeing the metrics of our job. So let me refresh this and say last 30 minutes. So you can see maybe last 1 hour, a bit more, yeah. So you can see all the utilization of your jobs. And if you actually see The GPU metrics, you see a little up in the GPU because earlier the GPU is idle, we were doing nothing. And here you see a tiny bump in the GPU at the point of my cursor. This was where we ran that one epoch to see the time. So you can actually see at what point of time your GPU is active, what it's doing, when is it idle and stuff like that. And now since I'm already running a job, it is showing. If I refresh this again, I'll see the progress happening because my job is running. And with 16 epochs, I want to see how much of my GPU memory is being utilized. About with batch size of 16, I'm utilizing a max of 13 GB. About 13 GB here, and that's what is reflected here. It's the same, about 13 GB, but this is another way to monitor your job. So if you keep running this, for instance, it became 1 MB because the job is done. If you come back here and see your job is completed, so you would see it'll go back to 0. So with NVIDIA SMI, if you're using this option, make sure that you look into the profiling of your job while your job is running. If your job is completed, NVIDIA SMI will not show you anything because it's like it literally is invoking your GPU to get its current state. So the current state of GPUs, it's not active, you're not utilizing anything. GPU 0, we saw, right? The CUDA core count or the MPI rank that we saw was 0 for this particular command. For this particular command here that we used, echo CUDA device, whatever command, it said 0, so that is 0. If you have more than 1, you'll see one more block and it shows 1 and how much utilization is happening there. But currently this GPU is not utilized at all, so you'll see 0. But let's say you ran a job yesterday and you want to look at the stats of the job today, then maybe NVIDIA SMI is not for you. You'd rather go to Grafana and look at Grafana tools and see how your job did. See here, because you can see the history of the job here in Grafana than NVIDIA SMI. But NVIDIA SMI is a really cool tool when you're actually parallelly running your job with different dynamic workloads and want to exactly see what is happening. Than, mapping here is saying, this is now I'm doing, so I don't know. So you have to map the timeline here. So based on how and when you want to profile, you can switch between NVIDIA SMI and this. But now you might ask, hey, NVIDIA SMI is telling me how my GPU is doing, but what about my CPU? Because here, if I see my CPU usage, it went up to like 25%, which is really good because I only asked for 10 CPU cores and not 80 CPU cores. That Ascent has like about 80 CPU cores. I'm not asking for all. I'm only getting for 10, and utilization of that 10 is like 25%, which is not bad. So it means that I can literally go with 3 or 4. And I'll tell you how you can do those modifications as well. But the maximum memory I'm using is 503 GB. And here is where my code is coming into picture, the code setup for running the particular compute node. Like once they launch the compute node, they write their own directives and everything in that compute node. So even when you're not running any load, you see that you have a utilization of about 74 GB here. So this particular node can go up to 512 MB, which is like the max utilization. And we have been using only 145 GB. So that is for 10 compute hours 10 compute nodes that we are looking at. Amit, go ahead, please.
Yeah, I had a quick question. So here when you say node, that means only one GPU, right?
This particular instance is actually CPU showing you the entire node and what you as a user are doing. Let's say if you and me are 2 users on the same node, it'll show user 1 and user 2. So the node is still the entire node, but then the stats that you're getting is for your job on that node. So for instance, let's go to Ascend here and see what is this CPU utilize. So currently I'm in Ascend, I'm on this node, not on the bigger node. So let's look at the configurations of this node. So I'm in this dual GPU compute node, this one. And the maximum memory I can use is 412 GB for the entire node. Let's say if 3 people are using that node, not just me, all 3 of us together can only use 472 GB of RAM memory or memory for the RAM or main memory, whatever we call it. For me, so the question that you asked is if it's just me, I still can't I should not like basically what technique that OSC uses is called backfill. So how they allocate resources is based on how many nodes you ask for, like how many n tasks per node or how many CPU cores you ask. They say if you ask, say, for one CPU core, then they say per CPU core, you can ask for maximum memory of X. For instance, batch limits, if we actually go for batch limits. So slur mitigation page. Let's see if this is the one.
So one quick question. Like I wanted to understand the hierarchy. So basically SN or Pitzer or any of them are basically the cluster, right?
Yes.
And each cluster has the nodes that you were showing in the previous diagrams, which may have like smaller nodes or bigger, larger nodes, right?
Yes.
And then each node may have multiple GPUs, like 4 GPUs or 2 GPUs, depending on, I mean, I think so the
What
configuration.
configuration they have. Yes.
Yeah, yeah, but when we are using, like for example, you were showing the dashboard that shows the performance of only one GPU or all the all GPUs combined.
Shows all GPUs combined based on which endpoint you're hitting. For instance, here I am hitting the endpoint called jobs, HPC job metrics, but there are other
Mhm.
endpoints. For instance, on-demand clusters. Let me go to on-demand cluster. So you can go see the same thing from different views. When you view it from the job perspective, they'll fetch, or so they have an entire Prometheus database at the back end, and the query only fetches the utilization of your job on that particular node. Though the entire metrics there you see is the entire node, like the max line you see is for the full node, but the green line that you see is your utilization. If two people are using it, you'll see maybe a green line and a yellow line showing two different people using the same.
I see. Okay, that's like users, end users utilization.
Yes. So for instance, this is Ascent node, and previously what we saw, I can show you side by side how two views of that will change. And also when you're using NVIDIA SMI, it will show you the entire node, all four, because that's not configured very thoroughly when, I mean,
Yeah,
when
but that also gives us like the GPU wise, like GPU 0 and then GPU
yeah, for
1.
instance, let's say I'm running NVIDIA SMI and there are like 4 GPUs currently allocated. It might show all 4 GPUs, but I have to know which GPUs are allocated to me to see where it goes. So profiling can get a little confusing there. So first you have to know which GPU is allocated to you, then look for the metrics of that particular GPU. It's same like you go to a railway station and there are tons of trains, right? Then you look at your ticket to see which train is yours, then you see where is your train, right? Something similar. So here is SN, and let me go back and fetch my job ID. Fetch my job ID. This is my job ID. So here I'm having a job ID point of view. So I'm just stretching it like this. So this view is literally giving me what is my job ID, like what is the utilization of my job. Whereas there's another view here, and this view is ascent host. Here I am just going into host. And if you remember 0, 1, 2, or 1, 2, 5, what is my host? My host is this one. This is my host. So if I just put that host number here and hit enter, here you see the jobs, like number of jobs that ran on that particular host. But if I say last 30 minutes, probably I'm the only user using it. So you'll see the CPU metrics almost similar to the metrics that you see. CPU load here you see is as much like 25%. We saw, right? Maximum of 25% of CPU being used. So that is what you would see here, because probably in the last 1 hour, I'm the only user using it. But when the load of the systems get super, super, super heavy, that's when for currently I'm requesting 10 nodes, and Ascend literally has the node that I got access to in Ascend. This one, if you see 2 AMD 60 usable cores, 60 cores, I'm only asking for 10. And Amit, you say, hey, I also want a node, but I only need 40 CPU cores. And there's literally no other system available. Then they'll only do the backfill or node sharing when whatever you're requesting for is not available in their available configurations, like free configurations. In that case, they'll come back and see in the allocated systems, which node can also accommodate you. And that's when they come and say, I'm only using 10 cores and you need 40 more. So it's free. So they'll give you and me the core together. And that's when our workload might look something like this. So this is literally me running my job on the system, and then you can come and ask for your job. So this could be your job. So let's say this is memory of that node. So they ask us to be, so by default, how they give is, since I asked for 10 cores, they'll do 10 times 4. So maybe 40 GB to me. And since you ask for 40 cores, they'll do 160 GB for you. So something like that. They have a metric calculation. So that's the maximum amount of memory they recommend that you use. So when you actually fine tune for cores, you also have to have an understanding of how much memory you can ask. And I think since we are over time today, I'll just do how to look at Grafana and how to create batch script in the next session. If that works, we are probably super over time. It's like 7 minutes. But I will quickly conclude today's session with at least a couple of points. Like I'll run one more job and I'll tell you what we can do before. So as now we saw different ways of interacting with it and seeing how we look at a particular job and execution. So in this case, when I actually see my GPU metrics, so this is how much am I using my GPU? Maybe the max GPU I'm going for is about 15 GB. I can still go up to like 80 GB. So maybe the batch size that I have, I can amplify the batch size. So that could be one way. So when you're actually wanting to fine tune and say, hey, I don't know which batch size I want to go, because one of the biggest challenges people have is if you expand the batch size, say now let's say I want to run 256 as my batch size and I want to run it. You don't know if you can run it, but I'm pretty sure it will give you out of memory error because the batch size is super huge. But let's run that and see. Oops. Oh, sorry. I think I'm in the wrong node. So here, yeah. So it's trying to load, and most likely, I mean, when you span the batch size, you'll need more GPU memory. So by looking at the graph stats and looking at how much GPU memory is being utilized, you can have a ballpark estimation that when you want to run a full scale run in a batch mode, like when you want to create a file like this, you exactly know what you can give here. So you can use interactive mode to figure out what configurations or how you're running is utilizing CPUs, GPUs, to what extent is your GPU being utilized, to what extent is your memory being utilized. And see, I got the error as I expected, saying memory management issue. Because when I was running batch size of 16, my GPU utilization was around GPU metrics. Yeah. My GPU utilization when I was using 16 at 16 GB was around 13 GB. And I'm using only one core and one core of Ascend, one core of Ascend. When I go back to the documentation, I see that one CPU core, I can use a maximum of 40 GB. So when I'm using like say 15 GB, so Amit, that's the difference you see here, right? So here I'm looking at the entire node. And when I see the entire node, it says the maximum I can use is 80 GB. But that is not for my job. So that's why I have to look at job metrics. That's what is showing me what's the maximum I can use, the total I can use in my job. Because I requested for only one single GPU. Is that making sense? So
Yeah.
instead of looking at from the node. So this is if you see cluster metrics. So here you're looking at a node as a whole. But if you're at job metrics, you're seeing what your job is permitted to. So here the same node, I can see 40 here and 80 here because in here you're asking for only one GPU and the documentation clearly says for one GPU, you can't go beyond 40. So now if I have to scale, if I have to think about the scalability, 16 GB is letting me like say 30, maybe I can do into 3. Or into 3 might be super tight. So maybe I can go just into 2 and I can do 32. So now if I want to run my job, I can literally go just by looking at stats. I could tell that when I made 256, it will break because you can scale and see. Because now you know at 16 GB how much memory of your GPU is being used. So now I'm going 32 and it'll run nicely. So it will not break my code because I still have decent amount of memory in my GPU to run this instance. So since I don't have enough time to show and run, so let this run and I'll show you a couple of metrics of how changing files. So earlier in the current system, we are having our data sets and everything in this orange folder. So what I did in another experiment is even before running the experiment, after I got an allocation, like say after I got this node, I copied my entire data and test data into this system. And now I ran a particular bunch of jobs this way. So instead of giving my path here, I'm just giving temp directory, which is basically a local file in that particular node. And I'm saying here is where my data is, and write results also to my temp directory and run. And doing that will literally let you do instances like this. Wait, yeah. So when I ran that, so when I ran from my file system for one epoch, it was taking 2 minutes, 42 seconds. And the same one epoch is actually taking 2 minutes, 36 seconds, few less. I mean, since our networks are super advanced and my job is super tiny, you couldn't see a big difference. But when I made batch size of 1, you can see like about 1 minute of a difference in this scenario. So what technically is happening is whenever you're running, say, a batch size of 4 training loop, 4 images get copied from your disk space into your CPU RAM or main memory. And in the main memory, your CPU does data processing, converts those images into vectors and moves those vectors into GPU memory. And then that's where your weights and everything is computed. So for every batch, you literally have to go back to the file system, go through the file server and come back. And if there are like a ton of users constantly accessing file systems, you might face delays. So, but before you run the job, if you can, like when you submit a job, something like this, before you make a full submission, if you can literally copy, like, okay, this is in this setting, I couldn't show, but basically what you could do is if you can actually copy your entire workflow, like this one. Yeah, this one. If you can copy wherever is your data into the temp directory of that particular node after you get the allocation, you can literally run. And whenever you're running, you are storing instead of shared file system, you have your entire data in your local box. So from local box, it goes into main memory to CPU. So you can avoid all the network traffic and it's simply local traffic. And you can speed up your training job. And you can also see that, for instance, my entire data set is about maybe 10 or 14 GB size. So my temp storage, like each node here that you see, each node has its own local storage, like how your laptop has a local storage. Each node has a local storage, and that local storage is also pretty decent. So the current node that I'm running can store up to 1.92 TB of local data, and I'm only needing 14 GB. So imagine, let's say you have billion files that you want to process, spend some time, copy the files and one go to the internal storage and then start processing from there and you'll be able to see a good speed up. So anybody on this current call have such a scenario? We can test with your code and see. We can set that up and test that for your training job and see. Anyone? Okay, maybe I'll send out an email to Jenna and see if she has that workload. But that is one of the ways where you can literally speed up your training job, is copying the entire data into that particular node and do it. So the game here is understanding how entire HPC interactions happen and then gaming the system so you can do your workload faster and more efficiently. Any questions on this one? So again, I forgot what I was running this for. So yeah, so I knew this one will be running. So as I said, right now I went from 256 to 32 and my job ran to success. And I can literally go back to Grafana and see this happening. So if I refresh my page, you could actually visually see the memory utilization of Grafana. Let's see, last 30 minutes. Last 1 hour. Yeah, so this was when we were running at 16 and this was when we were running at 32. So we can still maybe go like 40 if you want to. So you still have some memory left. So having an understanding of how utilization happens, you can scale up, speed up, because you're going from 16 to 32, you're reducing the execution time by half, at least about half. So here you were able to run in like 2 minutes and 45 seconds, while you still have precision of say 0.31. And if you see at 16, what was happening, code here. So where was 16? Yeah, at 16 you have about 30 precision, but the time was higher, slightly higher, because again GPUs are super fast, so you'll barely notice, but you'll see the differences when you're going with large batch sizes and larger images. So Any questions for today's session? Probably then I put more content than needed for the session. So in the next session, I'll probably go over on how you can look at those graphs and how you can change the batch script, or how you can compute the memory for the batch script, and how you can get down your costs at least by 30%, giving full allocation versus whatever job allocation that you have. And I'll probably reach out to, so I'll do the next session in about a month's time. So I'll give people enough time to have basic understandings of OSC, and also have a dry hands-on, at least with YOLO model, if they don't have their own models in the system. So I'll stop sharing, and this would be a good time if you have any questions.